Question 1. When conducting an energy audit for a municipal administrative complex, which factor, according to the principles outlined in ISO 50002, 2014, most critically influences the determination of the audit scope and the level of detail required for effective energy performance improvement recommendations, considering the public sector context and potential regulatory compliance obligations? Option A. The historical energy consumption data available for the past fiscal year without considering future operational changes. Option B. The total square footage of the administrative complex, irrespective of its functional zoning or operational hours. Option C. The number of energy auditors available to perform the audit, assuming a fixed budget for the assessment. Option D. The precise definition of the audit's objectives and the explicit inclusion of relevant national or regional energy efficiency mandates for public buildings. The correct answer is D. The precise definition of the audit's objectives and the explicit inclusion of relevant national or regional energy efficiency mandates for public buildings. Explanation. The core principle guiding the scope and depth of an energy audit for a government building, as per ISO 50002, 2014, is to ensure that the audit provides actionable insights for improving energy performance. This requires a systematic approach that considers the specific context of government operations, which often involve diverse building types, complex occupancy patterns, and public accountability mandates. Clause 4. 1 of ISO 50002 emphasizes the importance of defining the scope and objectives of the energy audit. For government buildings, this involves not only identifying energy-saving opportunities, but also ensuring compliance with relevant national and local energy efficiency regulations, such as those mandating reductions in public sector energy consumption or promoting the use of renewable energy sources. The audit must also consider the life cycle costs of proposed improvements, aligning with public financial management principles. Therefore, comprehensive audit for a government building would typically encompass a detailed analysis of energy consumption across all major end uses, an assessment of existing energy management practices, the identification of technically feasible and economically viable energy-saving measures, and the development of a prioritized action plan that accounts for regulatory requirements, budgetary constraints, and the specific operational needs of the government entity. The depth of the audit is directly proportional to the clarity of these defined objectives and the availability of reliable data. Question 2. When undertaking an energy audit for a large manufacturing facility, adhering to the principles of ISO 50002, 2014, which of the following approaches to initial data collection and analysis would best align with the standard's guidance for defining the audit scope and identifying significant energy uses? SU. Option A. Focusing initial efforts on identifying and quantifying all potential energy conservation measures, ECM, through a brainstorming session with the facility's engineering team, and then retrospectively collecting data to support the feasibility of the most promising ideas. Option B. Initiating with a thorough review of the organization's existing energy management system documentation, historical energy bills, production data, and conducting structured interviews with key personnel to gain a foundational understanding of energy flows and operational practices before proceeding to targeted measurements. Option C. Primarily relying on publicly available industry benchmarks and aggregated utility data for similar facilities to establish baseline energy intensity, supplemented by a brief site walkthrough to confirm operational assumptions. Option D. Conducting detailed, continuous sub-metering of all major energy-consuming equipment and processes for at least one full operational cycle, followed by complex statistical modeling to correlate energy consumption with production output and environmental variables. The correct answer is C. Primarily relying on publicly available industry benchmarks and aggregated utility data for similar facilities to establish baseline energy intensity, supplemented by a brief site walkthrough to confirm operational assumptions. Explanation. The energy audit process, as outlined in ISO 50002, 2014, emphasizes a systematic approach to identifying energy-saving opportunities. A crucial aspect is the selection of appropriate methodologies for data collection and analysis. While various protocols exist, such as those from ASHRAE or specific national standards, the core principle remains the same: to gather accurate and relevant information about energy consumption and its drivers. ISO 50002, 2014, in its guidance for conducting energy audits, stresses the importance of tailoring the audit scope and depth to the specific organization and its energy management system. This involves understanding the facility's operational characteristics, energy-using equipment, and existing monitoring capabilities. The standard advocates for a phased approach, typically starting with a preliminary review to define the scope and objectives, followed by a more detailed investigation of significant energy uses. The choice of data collection methods, whether through direct measurement, analysis of historical records, or interviews, depends on the audit's objectives and the availability of data. The analysis phase then involves interpreting this data to identify inefficiencies and quantify potential savings. ISO 50002, 2014 distinguishes between different levels of audit detail, from a general overview to a comprehensive investment-grade audit, each requiring different analytical tools and data granularity. The overarching goal is to provide actionable recommendations for improving energy performance, which necessitates a thorough understanding of the energy audit's context and the application of suitable analytical techniques. Question 3. Consider a large industrial facility that has recently undergone a significant upgrade to its primary production machinery. The facility's energy auditor is tasked with establishing a robust energy baseline for monitoring future performance improvements, as per ISO 50002, 2014 guidelines. The auditor has collected data on total annual energy consumption, annual production output, and average outdoor temperature for the past 5 years. Analysis of the data reveals a strong correlation between energy consumption and both production output and outdoor temperature. Which of the following approaches would be most appropriate for establishing the energy baseline, ensuring that the baseline accurately reflects the facility's energy performance independent of operational and climatic variations? Option A. Develop a regression model that relates total energy consumption to production output and average outdoor temperature, using the historical data to quantify the impact of each variable. Option B. Calculate the baseline by averaging the energy consumption from the 2 years prior to the machinery upgrade, excluding the most recent year's data. Option C. Establish the baseline solely based on the lowest annual energy consumption recorded in the past 5 years, assuming this represents optimal operational efficiency. Option D. Use the average annual energy consumption from the 3 most recent years as the baseline, assuming recent data is most representative. Correct answer is A. Develop a regression model that relates total energy consumption to production output and average outdoor temperature, using the historical data to quantify the impact of each variable. Explanation. Establishing an energy baseline is a critical first step in the energy auditing process, as outlined in ISO 50002, 2014. The baseline serves as a reference point against which energy performance improvements are measured. It is not merely a snapshot of past consumption, but a dynamic representation that accounts for significant influencing factors. These factors, often referred to as variables, can impact energy consumption independently of the organization's energy management efforts. Therefore, identifying and quantifying these variables is essential for accurate performance evaluation. Without this, any observed changes in energy consumption could be mistakenly attributed to energy management actions, when they are actually due to external influences. ISO 50002, 2014 emphasizes that the baseline should be established using historical data that is representative of the facility's operations and conditions. The process involves collecting data on energy consumption and relevant variables over a defined period. Statistical methods are often employed to develop a model that describes the relationship between energy consumption and these variables. This model allows for the normalization of energy consumption, enabling a fair comparison of performance over different periods, even when the influencing variables have changed. For example, if a manufacturing plant's production volume increases significantly, its energy consumption will likely rise. A properly established baseline, incorporating production volume as a variable, would account for this increase, allowing the auditor to determine if the energy intensity per unit of production has actually improved or worsened. The key is to isolate the impact of energy management from the impact of these external drivers. Question 4. An energy auditor reviewing a manufacturing facility's electricity bills over the past 3 years notices a consistent pattern. The total kilowatt-hour consumption has remained relatively stable, yet the total cost has increased by 15% year over year for the last 2 years. Production output has also seen a moderate increase of 5% annually. The facility operates under a tiered pricing structure with a demand charge component. Which of the following is the most likely primary driver for this observed cost escalation, assuming no significant changes in operational hours or production processes that would directly explain the increased demand charges? Option A. Escalating demand charges due to increased peak load intensity, even with stable overall consumption, potentially caused by simultaneous operation of high-draw machinery. Option B. A systematic error in the utility's metering equipment that has been consistently over-registering consumption over the past 2 years. Option C. The introduction of new, energy-efficient equipment that has subtly increased the overall baseline energy consumption, masked by production fluctuations. Option D. A decrease in the facility's power factor, leading to penalties from the utility provider without a direct increase in kWh consumption. The correct answer is A. Escalating demand charges due to increased peak load intensity, even with stable overall consumption, potentially caused by simultaneous operation of high-draw machinery. Explanation: the core of utility bill analysis within an energy audit, as guided by ISO 50002/2014, involves identifying trends and anomalies to pinpoint potential energy waste or inefficiencies. When examining a series of utility bills for a manufacturing facility, an auditor must look beyond simple consumption figures. Key performance indicators, KPI, are crucial for benchmarking and trend analysis. For instance, comparing energy consumption per unit of production, or per square meter of facility space, against historical data and industry benchmarks provides valuable insights. An unexpected increase in the cost per unit of energy, even with stable consumption, could indicate a change in tariff structures, a loss of a favorable rate, or an error in billing. Conversely, a significant rise in consumption without a corresponding increase in production or operational hours might signal equipment malfunction, poor operational practices, or energy leakage. The analysis should also consider external factors that might influence consumption, such as ambient temperature variations or changes in production schedules. The objective is to isolate the impact of these factors to accurately assess the facility's energy performance and identify areas for improvement, aligning with the systematic approach mandated by the standard. Question 5. During an energy audit of a large-scale chemical synthesis facility, an auditor identifies several potential energy-saving opportunities, ESO, related to optimizing reaction kinetics and separation processes. One ESO suggests modifying a distillation column's operating pressure to reduce steam consumption, while another proposes upgrading a heat exchanger network for improved thermal recovery. Considering the requirements of ISO 50002/2014 for evaluating ESOs, which approach should the auditor prioritize when assessing these identified opportunities to ensure their effective integration and long-term viability within the existing operational framework? Option A. Conduct detailed technical and economic feasibility studies for each significant ESO, considering their impact on process stability, product quality, and operational constraints. Option B. Recommend immediate implementation of all identified ESOs that show a positive simple payback period, irrespective of the complexity of integration or potential operational disruptions. Option C. Rank ESOs solely based on the projected annual energy savings, disregarding any potential impacts on production output or equipment lifespan. Option D. Focus on ESOs that require minimal capital investment and can be implemented quickly, even if their energy-saving potential is modest compared to other options. The correct answer is A. Conduct detailed technical and economic feasibility studies for each significant ESO, considering their impact on process stability, product quality, and operational constraints. Explanation: the question probes the understanding of process optimization techniques within the framework of ISO 50002/2014, specifically concerning the identification and prioritization of energy-saving opportunities, ESO, during an energy audit. The core principle being tested is how an energy auditor should approach the evaluation of potential ESOs derived from process analysis. ISO 50002/2014 emphasizes a systematic approach to identifying and evaluating ESOs. This involves not just listing potential improvements, but also assessing their feasibility, cost-effectiveness, and potential impact. The standard suggests considering technical, economic, and operational factors. When evaluating multiple ESOs from a complex industrial process, such as a chemical manufacturing plant, an auditor must move beyond simple energy reduction figures to consider the broader implications for the process itself. This includes understanding how an optimization might affect throughput, product quality, safety, and maintenance requirements. A critical step is to ensure that proposed optimizations are integrated into the overall operational strategy and do not create unintended negative consequences. Therefore, the most appropriate approach for an energy auditor is to conduct a comprehensive technical and economic feasibility study for each significant ESO, ensuring alignment with the organization's operational constraints and strategic goals. This detailed assessment allows for informed decision-making regarding the implementation of ESOs, prioritizing those that offer the best balance of energy savings, cost, and operational benefits, thereby ensuring the sustainability and effectiveness of the energy management system. Question 6. During an energy audit of a food processing plant utilizing a combined heat and power (CHP) system for electricity generation and process heat, which of the following methods would most accurately reflect the system's energy efficiency assessment as per ISO 50002, 2014, considering the need for a holistic view of energy flows and performance indicators? Option A. Relying exclusively on the manufacturer's stated maximum efficiency under ideal load conditions, without verifying actual operational performance. Option B. Averaging the reported efficiencies of individual components, e.g., boiler efficiency, turbine efficiency, without accounting for their integration and system-level losses. Option C. Solely focusing on the electrical efficiency of the generator set, ignoring the utilization of waste heat. As electricity is the primary product, Option D. Calculating the ratio of total useful electrical and thermal energy output to the total primary energy input, benchmarked against industry standard efficiency figures for similar CHP units, while also considering operational data variations. The correct answer is D. Calculating the ratio of total useful electrical and thermal energy output to the total primary energy input, benchmarked against industry standard efficiency figures for similar CHP units, while also considering operational data variations. Explanation: ISO 50002, 2014, specifically in its guidance on assessing energy performance of equipment and systems, emphasizes a structured approach. When evaluating the efficiency of a complex system, such as a combined heat and power (CHP) unit serving a manufacturing facility, the audit must consider the interplay of various energy streams and conversion processes. A key aspect is determining the overall system efficiency, which accounts for the primary energy input and the useful energy outputs in their respective forms, e.g., electrical, thermal. For a CHP system, efficiency is often calculated as the ratio of total useful energy output, electricity and usable heat, to the total primary energy input. However, a more nuanced assessment, as advocated by the standard, involves benchmarking against best available techniques (BAT) or similar installations, and considering the operational profile and load variations. The standard promotes the use of energy performance indicators, NPI, that are relevant to the specific equipment and system being audited. For a CHP unit, relevant NPIs might include electrical efficiency, thermal efficiency, and overall CHP efficiency, often expressed as percentages. The audit should also consider factors like auxiliary energy consumption, standby losses, and the degradation of performance over time due to wear and tear or suboptimal maintenance. The standard encourages the use of both direct measurements and indirect calculations based on manufacturer specifications and operational data. To accurately assess the efficiency of a CHP system in the context of ISO 50002, 2014, one must consider the total useful energy delivered relative to the total primary energy consumed, while also accounting for the operational context and potential for improvement through operational adjustments or technological upgrades. This requires a comprehensive understanding of the system's design, operation, and maintenance history. Question 7. During an energy audit of a manufacturing plant that has recently integrated a large-scale battery energy storage system, BESS, to manage its significant peak demand charges, what specific aspect of the BESS operation, as guided by the principles of ISO 50002, 2014, would an auditor prioritize for detailed investigation to identify the most impactful energy performance improvements? Option A. Cybersecurity protocols implemented for the best control system to prevent unauthorized access and operational disruptions. Option B. The thermal management system's efficiency in maintaining optimal battery operating temperatures, including fan power consumption. Option C. The chemical composition and degradation rate of the battery cells, as this directly impacts the long-term energy capacity. Option D. The best charge/discharge cycling strategy, and its correlation with the facility's real-time electricity tariff structure and operational load profile. Correct answer is D. The best charge/discharge cycling strategy and its correlation with the facility's real-time electricity tariff structure and operational load profile. Explanation: ISO 50002/2014 provides a framework for conducting energy audits. When evaluating a battery energy storage system, BESS, within an industrial facility as part of an energy audit, the auditor must consider various factors to ensure a comprehensive assessment. According to the principles outlined in ISO 50002, the audit should focus on identifying opportunities for improving energy performance. For a BESS, this involves understanding its operational characteristics, its role in the facility's energy system, and its potential for optimization. Key considerations include the best state of charge management strategy, its integration with renewable energy sources or grid services, and its impact on peak demand reduction. The efficiency of the BESS itself, including round-trip efficiency and parasitic loads, is also a critical area. Furthermore, the audit should assess how the BESS contributes to the overall energy management system of the facility, aligning with the objectives of ISO 50001. The selection of appropriate metrics and data collection methods is crucial for accurately evaluating the BESS performance and identifying actionable improvements. The audit process should also consider the specific regulatory landscape impacting energy storage systems within the relevant jurisdiction, such as grid interconnection standards or incentives for energy storage deployment. A holistic approach that examines the BESS from technical, economic, and operational perspectives is essential for a successful energy audit. Question 8. When assessing a manufacturing facility steam system as part of an energy audit compliant with ISO 50002/2014, what is the primary objective of the auditor regarding identified energy losses in components such as uninsulated steam mains and malfunctioning steam traps? Option A. Quantify the estimated magnitude of these energy losses and their contribution to overall system inefficiency for prioritization of improvement measures. Option B. To immediately recommend the replacement of all identified faulty steam traps and the installation of all unlagged piping without further analysis. Option C. To compile a comprehensive list of all potential steam system components that could experience energy loss, regardless of their perceived significance. Option D. To meticulously measure the exact thermal energy loss from each identified component using specialized calibrated equipment. Correct answer is A. To quantify the estimated magnitude of these energy losses and their contribution to overall system inefficiency for prioritization of improvement measures. Explanation: the question probes the auditor's responsibility in identifying and quantifying energy losses within a steam system, a core aspect of ISO 50002/2014. The standard emphasizes a systematic approach to energy auditing, which includes characterizing energy use and identifying opportunities for improvement. For steam systems, this involves understanding where thermal energy is lost. Common significant losses occur through uninsulated piping, inefficient steam traps, and excessive blowdown. The auditor must not only identify these qualitative issues, but also quantify their impact to prioritize corrective actions. This quantification is crucial for establishing a baseline and demonstrating the potential savings from proposed improvements. While visual inspection and component testing are vital, the ultimate goal is to translate these findings into an energy balance that highlights the magnitude of these losses. Therefore, the most comprehensive approach for an energy auditor, in line with the standard's intent, is to estimate the magnitude of these losses based on observable data and known system parameters, thereby providing a quantifiable basis for recommending specific interventions. This involves understanding thermodynamic principles related to heat transfer and steam properties to make reasonable estimations, even without direct measurement of every single loss point. The focus is on providing a robust, data-driven assessment of energy waste. Question 9. When evaluating the outcomes of an energy audit conducted according to ISO 50002, 2014, which specific activity most accurately represents the core function of the check phase within the Plan Do Check Act, PDCA cycle for continuous energy performance improvement? Option A. Developing a detailed action plan for implementing new energy-saving opportunities identified during the initial energy audit phase. Option B. Systematically reviewing energy performance data against established energy performance indicators and energy baselines to verify the effectiveness of implemented energy-saving measures. Option C. Implementing corrective actions based on the findings of the energy audit and communicating these changes to relevant personnel. Option D. Establishing the scope and objectives of the energy audit, including identifying the relevant legal requirements and organizational context. Correct answer is B. Systematically reviewing energy performance data against established energy performance indicators and energy baselines to verify the effectiveness of implemented energy-saving measures. Explanation. The Plan Do Check Act, PDCA cycle, is a fundamental iterative four-step management method used in business for the control and continuous improvement of processes and products. In the context of ISO 50002, 2014, which provides guidance on conducting energy audits, the PDCA cycle is crucial for systematically managing energy performance. The check phase is where the effectiveness of implemented energy-saving measures and the overall energy management system is evaluated. This involves reviewing the performance data collected against established energy performance indicators, NPI, and energy baseline, and assessing whether the planned improvements have been achieved. It also includes identifying deviations from the plan and understanding their causes. For instance, if an energy audit identified a potential saving from upgrading lighting to LED, the check phase would involve comparing the actual energy consumption of the lighting system post-upgrade with the predicted savings, considering factors like operational hours and occupancy. This comparison allows for the verification of the effectiveness of the implemented action and provides data for the ACT phase, which might involve standardizing the successful measure or initiating further improvements. Therefore, the core of the check phase is the systematic review and measurement of energy performance and the effectiveness of implemented actions. Question 10. Consider a scenario at a mid-sized manufacturing plant where an energy auditor is conducting a facility walkthrough survey as per ISO 50002, 2014. The auditor observes that several large centrifugal pumps, critical for the plant's cooling water system, are operating continuously at full speed, even during periods of low demand. Additionally, the auditor notices that the discharge valves on these pumps are partially throttled to regulate flow. Based on the principles of energy auditing during a walkthrough, what is the most likely primary energy inefficiency indicated by these observations? Option A. Frequent cycling of the pumps due to improper control logic. Option B. Oversizing of the pump motors relative to actual load. Option C. Inadequate insulation on the cooling water piping. Option D. Excessive throttling of discharge valves, leading to wasted pump energy. The correct answer is D. Excessive throttling of discharge valves leading to wasted pump energy. Explanation. The facility walkthrough survey, as outlined in ISO 50002, 2014, is a critical phase for an energy auditor to gather initial data and identify potential energy-saving opportunities. The standard emphasizes that the walkthrough should be systematic and cover all significant energy-consuming systems and areas within the facility. It is not merely a visual inspection, but involves active engagement with the site and its operations. A key aspect is to observe the actual operation of equipment and processes, noting their current settings, operating hours, and any visible signs of inefficiency such as leaks, poor insulation, or incorrect settings. The auditor should also interact with facility personnel to understand operational practices, maintenance schedules, and any perceived energy-related issues. Data collection during the walkthrough includes taking measurements where appropriate, documenting observations with notes and photographs, and collecting readily available information such as equipment nameplates and operational logs. The goal is to build a foundational understanding of the facility's energy performance and to inform the more detailed analysis that follows. This initial phase is crucial for framing the scope of the audit and prioritizing areas for deeper investigation, ensuring that the audit is tailored to the specific context of the facility. The systematic observation and documentation of operational parameters and equipment conditions are paramount to the success of this stage. Question 11. When an energy auditor identifies a significant opportunity to improve the efficiency of a primary heating system, what is the most crucial consideration for developing a comprehensive energy saving opportunity (ESO) proposal that aligns with ISO 50002, 2014 principles, beyond the direct energy savings of that system? Option A. The ease of implementation and minimal disruption to current production schedules, even if it limits the scope of savings. Option B. The potential cascading effects on other interconnected energy systems and the overall operational impact on the facility. Option C. The availability of specific government grants or subsidies that might be applicable to the identified technology. Option D. The immediate capital expenditure required for the proposed upgrade, irrespective of long-term operational benefits. The correct answer is B. The potential cascading effects on other interconnected energy systems and the overall operational impact on the facility. Explanation. The core of identifying energy-saving opportunities, ESO, within the framework of ISO 50002, 2014 involves a systematic approach that moves beyond simple identification of energy-consuming equipment. It requires an understanding of the interdependencies within an energy management system and the potential for cascading effects. When an energy auditor identifies a potential ESO, such as optimizing the operation of a boiler system, the subsequent steps must consider how this optimization impacts other energy-consuming or energy-producing systems. For instance, a more efficient boiler might lead to reduced steam demand, which in turn could affect the operation of steam-driven turbines or HVAC systems. Therefore, a comprehensive ESO proposal necessitates an analysis of these interdependencies and potential secondary impacts. This includes evaluating how the proposed change might alter operating parameters, maintenance schedules, or even the need for other equipment. The goal is to ensure that the proposed ESO, while targeting a specific area, contributes positively to the overall energy performance of the organization without introducing unforeseen negative consequences or requiring disproportionately complex supporting modifications. This holistic view, considering the system as a whole and its interconnected components, is paramount for developing robust and effective ESOs that align with the principles of continuous improvement mandated by energy management standards. The focus is on the strategic integration of identified opportunities into the broader energy management system, ensuring that the proposed changes are technically feasible, economically viable, and operationally sound within the existing organizational context and regulatory landscape. Question 12. When conducting an energy audit of a manufacturing plant's electrical system, adhering to the principles outlined in ISO 50002, 2014, what is the most effective initial approach for systematically identifying significant energy uses, SU, within the electrical distribution and consumption network? Option A. Comprehensive analysis of historical electricity bills, sub-metering data, and equipment operational logs to pinpoint major load centers and periods of high consumption. Option B. Implementing a blanket replacement of all older fluorescent lighting fixtures with modern LED technology across the entire facility as a precautionary measure. Option C. Direct visual inspection of all electrical panels and transformers for any visible signs of damage or overheating without prior data review. Option D. Conducting a series of short, on-site interviews with maintenance staff regarding their perceived major energy consumers. The correct answer is A. Comprehensive analysis of historical electricity bills, sub-metering data, and equipment operational logs to pinpoint major load centers and periods of high consumption. Explanation. The question pertains to the systematic identification and evaluation of energy-saving opportunities within an industrial facility's electrical distribution system, as guided by ISO 50002, 2014. Specifically, it focuses on the application of a systematic approach to identify significant energy uses, SU, within the electrical system, which is a foundational step in an energy audit. The audit process mandates the identification of SEUs to prioritize areas for improvement. In the context of an electrical system, this involves examining various components and their operational characteristics. The most effective method for identifying SEUs in an electrical system during an energy audit, as per the principles of ISO 50002, 2014, is through a detailed analysis of energy consumption patterns and operational data. This analysis would typically involve reviewing utility bills, sub-metering data, load profiles, and equipment specifications to pinpoint where the majority of electrical energy is consumed and where losses are likely to be significant. For instance, high-power continuous loads like large motors, extensive lighting systems, or HVAC equipment are prime candidates for SEUs. Furthermore, understanding the operational schedules and load factors of these components is crucial. The audit should also consider factors like power factor, harmonic distortion, and voltage levels, as these can indicate inefficiencies within the electrical distribution. The core principle is to move beyond general observations to a data-driven identification of the most impactful energy consumers and potential areas for optimization within the electrical infrastructure. Question 13. In conducting an energy audit according to ISO 50002-2014, what is the primary objective when segmenting energy consumption data into distinct operational categories, such as production lines, auxiliary systems, and building services, within a large industrial complex? Option A. Benchmark the facility's energy intensity against industry averages without the need for detailed internal analysis of specific energy-consuming equipment. Option B. To establish a baseline for energy performance indicators, NPI, and to identify the most significant energy uses, SU, for targeted improvement initiatives. Option C. To fulfill regulatory reporting requirements mandated by national energy efficiency laws, such as the Energy Performance of Buildings Directive. Option D. To simplify the overall energy management process by consolidating consumption data into easily manageable, high-level summaries. The correct answer is B. To establish a baseline for energy performance indicators, NPI, and to identify the most significant energy uses, SU, for targeted improvement initiatives. Explanation. The core principle of breaking down energy use in an energy audit, as outlined by ISO 50002-2014, is to identify significant energy uses, SU, and to quantify energy consumption across different operational areas, equipment types, or processes. This detailed breakdown is crucial for pinpointing where energy is being consumed most heavily and where the greatest opportunities for improvement lie. The standard emphasizes that the depth of this breakdown should be commensurate with the overall energy consumption and the potential for savings. A granular analysis allows for targeted energy management actions and more accurate measurement and verification of savings. For instance, a manufacturing facility might break down energy use by production line, by specific machinery, e.g., motors, HVAC, lighting, by building zone, or by process step. The objective is to move beyond a simple total energy bill to a detailed understanding of the energy flow within the organization. This informs the prioritization of energy-saving opportunities and forms the basis for setting energy performance indicators, NPI. Without this detailed understanding, efforts to improve energy efficiency might be misdirected or less effective. The breakdown facilitates the identification of anomalies, inefficiencies, and areas of significant waste that might otherwise be obscured in aggregated data. It supports the development of a robust energy management plan by providing the necessary data for decision-making. Question 14. An auditor conducting an energy audit at a manufacturing facility utilizing a high-temperature industrial dryer equipped with a heat recovery system for preheating incoming air needs to assess the overall energy efficiency. Considering the principles outlined in ISO 50002-2014 for industrial processes, which specific aspect of the dryer's operation and its associated heat recovery system requires the most meticulous scrutiny to identify significant energy-saving opportunities. Option A. The electrical power consumption of the dryer's conveyor belt and the noise levels generated by the exhaust fan. Option B. The ambient temperature surrounding the dryer and the frequency of operator access to the drying chamber. Option C. The thermodynamic efficiency of the heat exchanger in the recovery system and the insulation integrity of the dryer casing. Option D. The chemical composition of the material being dried and the drying time required for a batch. Correct answer is C. The thermodynamic efficiency of the heat exchanger in the recovery system and the insulation integrity of the dryer casing. Explanation. The core principle of ISO 50002-2014 concerning energy audits in industrial processes is the systematic identification and evaluation of energy use and consumption. This involves a phased approach, starting with planning and data collection, moving to an on-site investigation, and culminating in reporting and follow-up. During the on-site investigation phase, the auditor must thoroughly examine the energy performance of specific equipment and systems. For an industrial dryer operating at a high temperature and employing a heat recovery system, the auditor needs to assess the efficiency of both the primary heating mechanism and the effectiveness of the heat recovery unit. The efficiency of the dryer itself is influenced by factors such as heat loss through insulation, the effectiveness of air circulation, and the dryer's operational parameters relative to the material being processed. The heat recovery system's performance is evaluated by comparing the temperature of the exhaust stream before and after heat exchange, and the amount of heat transferred to the incoming air or another process stream. ISO 50002 emphasizes a holistic view, considering how different components interact. Therefore, the most critical aspect for an auditor to scrutinize in this scenario is the overall energy balance and the potential for optimizing the heat transfer within the recovery system, as this directly impacts the primary heating load and overall energy consumption. This involves understanding the thermodynamic principles governing the process and identifying deviations from optimal performance. Question 15. When evaluating the economic viability of proposed energy conservation measures identified during an ISO 50002/2014 compliant energy audit, which financial assessment criterion, by accounting for the time value of money and the entire project lifecycle, offers the most comprehensive insight into the investment's true profitability and is therefore preferred for strategic decision-making over simpler, non-discounted methods? Option A, simple payback period. Option B, net present value (NPV). Option C, annual energy savings. Option D, return on investment (ROI). The correct answer is B, net present value (NPV). Explanation: the economic analysis of energy conservation measures, ECOM, within an energy audit, as guided by ISO 50002/2014, requires a comprehensive understanding of financial metrics beyond simple payback. While simple payback is a straightforward metric, it fails to account for the time value of money and the entire lifespan of an investment. More sophisticated methods like net present value (NPV) and internal rate of return (IRR) are crucial for evaluating the true profitability of ECMs. NPV discounts future cash flows back to their present value, considering a specified discount rate that reflects the cost of capital or opportunity cost. A positive NPV indicates that the project is expected to generate more value than it costs. IRR, on the other hand, is the discount rate at which the NPV of all cash flows from a particular project equals 0. It represents the effective rate of return generated by an investment. When comparing multiple ECMs, or when making investment decisions under capital constraints, these metrics provide a more robust basis for selection than simple payback alone. The selection of an appropriate discount rate is a critical input for NPV calculations and influences the decision-making process. ISO 50002/2014 emphasizes the importance of presenting economic viability clearly to stakeholders, enabling informed decisions on implementing energy efficiency improvements. The focus is on demonstrating the financial benefits and ensuring that chosen measures align with organizational financial objectives. Question 16. An energy auditor is evaluating a large manufacturing facility's lighting system, which currently uses legacy high-intensity discharge (HID) lamps in production areas and fluorescent tubes in office spaces. The facility operates 24/7, with varying occupancy levels across different zones. The auditor is tasked with recommending a comprehensive lighting upgrade strategy aligned with ISO 50002/2014 principles. Which of the following approaches best addresses the holistic assessment and potential for significant energy savings, considering both technological advancements and operational realities? Option A. Advocate for the installation of a sophisticated, fully integrated daylight harvesting and network dimming system across the entire facility, including production areas, without a detailed analysis of the return on investment for each component. Option B. Recommend a phased upgrade, starting with replacing office fluorescent tubes with standard LED tubes and only considering motion sensors in intermittently used areas, deferring any significant upgrades in production zones due to their 24/7 operation. Option C. Focus solely on replacing all existing lamps with the lowest wattage LED equivalents available on the market to achieve immediate cost reduction, without considering lighting controls or specific area requirements. Option D. Prioritize the replacement of all HID and fluorescent lamps with equivalent lumen output LEDs, and implement a zone-based occupancy sensing system across all production and office areas, coupled with a centralized dimming schedule based on historical production data. Correct answer is D. Prioritize the replacement of all HID and fluorescent lamps with equivalent lumen output LEDs, and implement a zone-based occupancy sensing system across all production and office areas, coupled with a centralized dimming schedule based on historical production data. Explanation: the primary objective when assessing a lighting system upgrade for energy efficiency, as guided by ISO 50002/2014, is to identify opportunities for significant energy savings and improved operational performance. This involves a thorough analysis of the existing lighting infrastructure, including the type of lamps, their operating hours, lumen output, and the presence and effectiveness of control systems such as occupancy sensors or daylight harvesting. The standard emphasizes a systematic approach to identify energy-saving opportunities, ESO. When considering a transition to LED technology, the evaluation must extend beyond simple wattage reduction. It necessitates a comprehensive understanding of the total cost of ownership, including initial capital expenditure, maintenance savings, and the potential for enhanced light quality or controllability. Furthermore, the integration of advanced lighting controls, such as network systems that allow for dimming based on occupancy and ambient light levels, can yield substantial additional savings beyond the inherent efficiency of LEDs. The selection of the most appropriate upgrade path requires a nuanced understanding of the specific operational context, including the functional requirements of different spaces, the potential for behavioral changes among occupants, and the alignment with broader organizational energy management objectives. The ultimate goal is to recommend a solution that not only reduces energy consumption, but also provides a favorable return on investment and meets the qualitative needs of the facility. Question 17. An industrial facility seeking to initiate an energy management program decides to conduct an initial assessment of its energy consumption. The objective is to quickly identify major areas of energy loss and implement immediate, low-cost improvements. This assessment involves a brief site visit, visual inspection of key equipment, and interviews with operational staff to understand basic energy usage patterns. No extensive data logging or detailed engineering calculations are performed at this stage, which type of energy audit, as conceptualized within the framework of ISO 50002/2014, best describes this initial effort. Option A, performance verification audit. Option B, walkthrough audit. Option C, investment grade audit. Option D, detailed energy audit. The correct answer is B, walkthrough audit. Explanation: the core distinction between different types of energy audits, as outlined in standards like ISO 50002/2014, lies in their depth of analysis, scope of investigation, and the level of detail provided for energy-saving opportunities. A walkthrough audit is typically a preliminary assessment, characterized by a brief site visit and visual inspection to identify obvious energy waste and low-cost, no-cost measures. It provides a general overview and is less data-intensive. A detailed audit, on the other hand, involves a more thorough examination of energy consumption patterns, equipment performance, and operational practices. It requires significant data collection, analysis, and often involves measurements. This type of audit aims to identify a broader range of energy-saving opportunities, including those with moderate capital investment, and provides more quantitative estimates of savings and costs. An investment-grade audit (IGA) represents the highest level of detail and rigor. It is specifically designed to provide sufficient information for financial decision-making and investment. IGAs involve detailed engineering calculations, life cycle cost analysis, and often the development of a comprehensive business case for proposed energy efficiency projects. They are typically commissioned when significant capital expenditure is being considered, and the accuracy of the projected financial returns is paramount. Therefore, an audit that focuses on preliminary identification of readily apparent energy waste and simple operational adjustments, without extensive data analysis or detailed financial projections, aligns with the characteristics of a walkthrough audit. Question 18. When conducting an energy audit according to ISO 50002, 2014, what is the most fundamental prerequisite for establishing a meaningful and actionable energy performance indicator, NPI, for a specific significant energy use? Option A. The establishment of a dedicated energy management team with defined roles and responsibilities. Option B. The availability of historical energy consumption data spanning at least 5 years for benchmarking purposes. Option C. The development of a detailed energy management plan that outlines specific energy-saving targets. Option D. Comprehensive identification and analysis of the significant energy use and the variables that influence its energy performance. The correct answer is D. Comprehensive identification and analysis of the significant energy use and the variables that influence its energy performance. Explanation. The development of relevant energy performance indicators, NPI, is a cornerstone of effective energy management systems, as outlined in ISO 50002, 2014. NPIs are quantifiable measures used to track and assess energy performance. For an NPI to be truly effective and align with the principles of ISO 50002, it must be established based on a clear understanding of the energy use and consumption of the facility or process being audited. This involves identifying the significant energy uses, SU, and understanding the key variables that influence them. ISO 50002 emphasizes that NPIs should be subject to review and refinement as understanding of energy performance evolves, and as changes occur within the organization or its operating environment. The standard stresses that NPIs should be correlated with the identified SEUs, and that the variables influencing them, known as variables influencing energy performance, must also be considered. This correlation allows for the accurate assessment of energy performance changes and the effectiveness of implemented energy-saving measures. Establishing an NPI without this foundational analysis of SEUs and their influencing variables would lead to an indicator that may not accurately reflect actual energy performance or be responsive to management actions. For instance, an NPI for a manufacturing plant that only measures total electricity consumption without considering production volume, a key influencing variable, would be misleading, as increased production would naturally lead to higher consumption, masking any efficiency improvements. Therefore, the most critical prerequisite for establishing a robust NPI is the thorough identification and analysis of significant energy uses and the variables that influence them, ensuring the NPI is both relevant and actionable. Question 19. When presenting findings from an energy audit to a manufacturing firm aiming to upgrade its HVAC systems, what approach to discussing financing options for the proposed energy conservation measures best aligns with the principles of ISO 50002, 2014 for facilitating informed strategic decision-making? Option A. Detail the projected payback periods and internal rates of return for each viable financing mechanism, explicitly linking the financial benefits to the company's stated strategic goals for operational cost reduction and carbon footprint minimization. Option B. Discuss the technical specifications of the proposed upgrades and their energy-saving potential, deferring all financial and financing discussions to a separate, subsequent meeting with the finance department. Option C. Present a simplified cost-benefit analysis for each proposed measure, emphasizing the lowest initial investment cost regardless of long-term operational implications or the availability of performance-based financing structures. Option D. Provide a comprehensive list of all available government grants and subsidies, focusing solely on maximizing the upfront capital available for project implementation, without detailing the long-term financial commitments or operational impacts. The correct answer is A. Detail the projected payback periods and internal rates of return for each viable financing mechanism, explicitly linking the financial benefits to the company's stated strategic goals for operational cost reduction and carbon footprint minimization. Explanation. The question pertains to the financial viability and strategic alignment of energy efficiency projects within the framework of an energy audit, as guided by ISO 50002, 2014. When evaluating financing options, an energy auditor must consider not only the direct financial returns, but also the broader implications for the organization. A key aspect is the integration of energy performance improvement with the organization's overall strategic objectives and capital allocation processes. This involves understanding how different financing mechanisms, such as internal funding, third-party financing, e.g., energy performance contracts (EPCs), or government grants, align with the company's risk appetite, cash flow patterns, and long-term investment horizons. Furthermore, the auditor needs to assess the impact of these financing choices on the project's payback period, return on investment (ROI), and net present value (NPV), ensuring these metrics are presented in a way that facilitates informed decision-making by management. The most effective approach balances financial prudence with strategic goals, ensuring that energy efficiency investments contribute to the organization's competitive advantage and sustainability targets. This involves a holistic view that goes beyond simple cost-benefit analysis to encompass strategic fit and the potential for creating long-term value. Question 20. When structuring an energy performance contract (EPC), following the principles outlined in ISO 50002-2014, what is the primary function of the energy baseline in relation to measuring the impact of implemented energy conservation measures (ECOM)? Option A. To establish a verifiable reference point for energy consumption and costs against which post-implementation performance is compared to quantify savings. Option B. To determine the initial capital investment required for the ECMs by calculating the total energy expenditure before any improvements. Option C. To provide a historical overview of all energy-consuming equipment within the facility, irrespective of their operational status. Option D. To serve as a contractual guarantee for the ESCO regarding the minimum achievable energy savings, regardless of operational changes. The correct answer is A. To establish a verifiable reference point for energy consumption and costs against which post-implementation performance is compared to quantify savings. Explanation. In the context of energy performance contracting (EPC), as applied within the framework of ISO 50002-2014, the concept of a baseline is fundamental. Baseline represents the energy consumption and associated costs for a defined period prior to the implementation of energy conservation measures (ECOM). ISO 50002-2014 emphasizes the importance of establishing a robust and verifiable baseline to accurately measure the performance improvements achieved through the implemented ECMs. The baseline must account for relevant variables that can influence energy consumption, such as production levels, operating hours, climate conditions, and occupancy. The accuracy and representativeness of the baseline directly impact the calculation of savings and the overall success of the EPC. Without a well-defined and adjusted baseline, it becomes impossible to definitively attribute energy savings to the ECMs, potentially leading to disputes between the energy service company (ESCO) and the client. The standard guides auditors in developing methodologies for baseline establishment and adjustment, ensuring that any changes in operational parameters are accounted for to provide a fair comparison between the pre- and post-implementation periods. This ensures that savings are not artificially inflated or deflated due to external factors, thereby upholding the integrity of the performance contract. Question 21. Consider an industrial facility seeking to establish a robust energy baseline for its primary manufacturing process, as mandated by the initial phase of an energy audit conducted under ISO 50002-2014. The facility has collected extensive historical data on energy input, production volume, ambient temperature, and operating hours over the past 3 years. The audit team's objective is to develop an energy model that can accurately predict the process's energy consumption under varying production schedules and seasonal temperature fluctuations, enabling the assessment of future energy efficiency projects. Which modeling approach would be most appropriate for this specific objective? Option A. Utilizing a qualitative expert judgment model based on the collective experience of the facility's long-serving engineers. Option B. Implementing a simple linear extrapolation of past energy consumption trends without considering influencing factors. Option C. Developing a statistical regression model that correlates energy consumption with key operational and environmental variables. Option D. Creating a detailed, first principles thermodynamic model of each individual piece of equipment within the process. The correct answer is C. Developing a statistical regression model that correlates energy consumption with key operational and environmental variables. Explanation. The development of energy models as described in ISO 50002, 2014 is crucial for understanding energy consumption patterns and identifying potential improvements. A fundamental aspect of this is selecting appropriate modeling techniques that align with the audit's objectives and the available data. When aiming to establish a baseline energy consumption that accurately reflects typical operational conditions and can be used to predict future energy use under various scenarios, a statistical approach that utilizes historical data to identify relationships between energy consumption and key influencing factors is most suitable. This allows for the quantification of energy performance and the evaluation of the impact of potential energy-saving measures. Such models often involve regression analysis to establish these relationships, providing a robust basis for comparison and forecasting. The goal is to create a representation that is both statistically sound and practically applicable for decision-making within the energy management system. Question 22. An energy auditor is tasked with evaluating a large industrial facility's cooling water system, which is critical for process cooling. The system comprises multiple cooling towers, pumps, and extensive piping. According to the principles outlined in ISO 50002, 2014 for conducting energy audits, what is the most crucial initial step in assessing the operational efficiency of this complex cooling water system to identify potential energy-saving measures? Option A. Conducting a thorough chemical analysis of the cooling water to identify potential scaling or corrosion issues without first quantifying the overall system's energy performance. Option B. Establishing a detailed operational baseline by collecting and analyzing historical and current data on water flow rates, temperatures, inlet, outlet, approach, pump power consumption, and ambient conditions, then comparing this to design parameters and industry benchmarks. Option C. Immediately recommending the replacement of older, less efficient pumps with variable frequency drives, VFD, based on the assumption that fixed-speed operation is inherently wasteful. Option D. Focusing solely on the cooling tower fan motor efficiency, assuming this component is the primary driver of energy consumption in the entire cooling water loop. The correct answer is B. Establishing a detailed operational baseline by collecting and analyzing historical and current data on water flow rates, temperatures, inlet, outlet, approach, pump power consumption, and ambient conditions, then comparing this to design parameters and industry benchmarks. Explanation. The question probes the understanding of how to systematically evaluate and improve the efficiency of a cooling water system as part of an energy audit, aligning with ISO 50002, 2014 principles. The core of such an evaluation involves assessing the system's performance against established benchmarks and identifying deviations that indicate inefficiency. For a cooling water system, key performance indicators, KPI, often include the temperature difference across the cooling tower, approach temperature, the water flow rate, and the energy consumed by pumps. A critical aspect of ISO 50002, 2014 is the focus on data collection and analysis to identify energy-saving opportunities. This involves not just looking at instantaneous values, but also understanding trends and correlations. For instance, an increasing approach temperature in a cooling tower, while maintaining similar ambient conditions, suggests reduced heat transfer efficiency, which could be due to fouling, scaling, or poor airflow. Similarly, excessive pump operation beyond what is required for the cooling load points to potential control issues or oversizing. The standard emphasizes a structured approach to identifying and prioritizing these opportunities. Therefore, the most comprehensive and effective initial step in an energy audit of a cooling water system, as per the standard's intent, is to establish a baseline of current performance using relevant operational data, and then compare this baseline against design specifications or industry best practices to pinpoint areas of significant energy waste. This systematic comparison allows for targeted investigation and the development of appropriate corrective actions. Question 23. When evaluating potential energy-saving opportunities within a manufacturing facility, as guided by ISO 50002, 2014, which principle is paramount for ensuring the audit's credibility and the reliability of its recommendations, particularly concerning the establishment of a robust energy baseline? Option A. Establishing a clear, documented, and representative energy baseline that accurately reflects historical energy consumption patterns and the operational context prior to any proposed interventions. Option B. implementing a rapid assessment approach that relies on generalized industry benchmarks rather than site-specific data for quantifying potential savings. Option C, prioritizing the identification of the most technologically advanced energy-saving measures, irrespective of their immediate applicability or cost-effectiveness for the facility. Option D, focusing solely on operational changes that require minimal capital investment, even if they do not address the most significant sources of energy waste. The correct answer is A, establishing a clear, documented, and representative energy baseline that accurately reflects historical energy consumption patterns and the operational context prior to any proposed interventions. Explanation: ISO 50002, 2014, Energy Audits, Requirements with Guidance for Use, provides a framework for conducting energy audits. While it does not prescribe specific calculation methodologies for energy savings, it emphasizes the importance of a systematic approach to data collection, analysis, and reporting. The standard outlines different levels of energy audits, from a preliminary review to a detailed investment-grade audit. The identification and quantification of energy-saving opportunities, ESO, are central to the audit process. The standard highlights the need to establish a baseline of energy use, and then to assess potential improvements against this baseline. This involves understanding the factors influencing energy consumption, such as operational parameters, equipment performance, and environmental conditions. The verification of savings from implemented measures is also a critical component, ensuring that the projected benefits are realized. The standard encourages the use of appropriate tools and techniques for data analysis, which may include statistical methods, energy modeling, or process simulation, depending on the complexity of the facility and the ESOs identified. The focus is on providing actionable recommendations that are technically feasible, economically viable, and environmentally sound, thereby contributing to improved energy performance. The standard's guidance on reporting ensures that findings are clearly communicated to stakeholders, facilitating decision-making regarding energy management. Question 24. When conducting an energy audit on a manufacturing facility, the audit team identifies a critical centrifugal pump operating in a production line. The available historical data on the pump's energy consumption is fragmented, and its original design specifications are not readily accessible. To accurately determine the pump's current energy efficiency and identify potential savings, which of the following approaches would be most appropriate according to the principles outlined in ISO 50002, 2014 for assessing equipment efficiency? Option A, analyze the pump's maintenance logs to identify any recurring issues or repairs that might indicate underlying inefficiencies. Option B, benchmark the pump's energy consumption against the average energy usage of similar pumps found in other facilities within the same industry sector. Option C, compare the pump's actual measured power input under specific operating conditions, e.g., flow rate, head, against its theoretical performance curves or manufacturer-provided performance data for similar models. Option D, calculate the total electrical energy consumed by the pump over the past year and divide it by the total volume of fluid pumped during that period. The correct answer is C. Compare the pump's actual measured power input under specific operating conditions, e.g., flow rate, head, against its theoretical performance curves or manufacturer-provided performance data for similar models. Explanation: the question probes the understanding of how to assess the energy performance of an existing piece of equipment within the framework of ISO 50002, 2014. The standard emphasizes a systematic approach to identifying energy-saving opportunities. When evaluating a specific piece of equipment, such as a pump, the most effective method to determine its current energy efficiency, especially when baseline data is limited or inconsistent, is to compare its actual energy consumption under defined operating conditions against its theoretical or design performance. This involves understanding the equipment's operational parameters and its intended function. ISO 50002, 2014, in its guidance on energy auditing, stresses the importance of understanding the as-is state of energy use. For a pump, this would mean understanding its flow rate, head, and the power it draws. Comparing this actual operational data to the pump's characteristic curves or manufacturer specifications, which represent its design or expected performance, allows for a direct assessment of its efficiency. This comparison highlights deviations and potential areas for improvement. Other methods, while potentially useful in broader energy management contexts, are less direct for a singular equipment efficiency assessment within the audit scope. For instance, simply reviewing maintenance logs provides historical context, but not a direct efficiency measurement. Benchmarking against similar equipment in the industry is valuable for broader strategic planning, but doesn't isolate the specific efficiency of the audited unit without detailed operational data. Calculating the total energy consumed over a period without reference to output or operational conditions provides a measure of usage, not efficiency. Therefore, comparing actual operational performance to design or theoretical performance is the most direct and informative method for assessing the energy efficiency of a specific piece of equipment, as per the principles of ISO 50002, 2014. Question 25. During an energy audit of a large commercial facility, the auditing team identified significant variations in supply air temperatures and occupant complaints regarding thermal discomfort in various zones. While the Central Air Handling Unit, AHU, was functioning within its design parameters, the air distribution network showed evidence of uneven airflow delivery. Considering the principles of ISO 50002, 2014, and the need to optimize HVAC energy performance, what is the most critical step to address these observed imbalances in the air distribution system? Option A. Increase the overall fan speed of the air handling unit to force more air through the system, thereby attempting to equalize conditions. Option B. Immediately replace the existing air handling unit with a more energy-efficient model to compensate for perceived system inefficiencies. Option C. Focus solely on improving the building envelope's thermal insulation to reduce the impact of uneven air distribution on occupant comfort. Option D. Perform a comprehensive airflow measurement and balancing procedure to adjust terminal devices and ductwork dampers according to the original design specifications or updated load calculations. The correct answer is D. Perform a comprehensive airflow measurement and balancing procedure to adjust terminal devices and ductwork dampers according to the original design specifications or updated load calculations. Explanation. The core principle of air distribution system balancing, as relevant to an energy audit under ISO 50002, 2014, is to ensure that the designed airflow rates are delivered to each conditioned space efficiently. This involves adjusting system components to achieve the intended air distribution, which directly impacts the performance of heating, ventilation, and air conditioning, HVAC systems. Inefficient balancing can lead to overconditioning in some areas and underconditioning in others, resulting in wasted energy due to excessive fan operation, unnecessary heating or cooling, and compromised occupant comfort. The process aims to minimize pressure drops and fan energy consumption, while meeting the specific thermal load requirements of each zone. This is achieved by carefully regulating dampers, diffusers, and other terminal devices. The objective is to align actual system performance with the design intent, thereby optimizing energy use and operational efficiency. This aligns with the energy audit's goal of identifying and quantifying energy-saving opportunities. Question 26. Which phase of the energy management system (NMS) development, as conceptualized within the framework of ISO 50002, 2014, most directly involves the rigorous evaluation of established energy baselines and the assessment of implemented energy-saving measures against their projected outcomes? Option A. The do phase. Option B. The plan phase. Option C. The check phase. Option D. The act phase. The correct answer is C. The check phase. Explanation. The core of establishing an effective energy management system, NMS, as outlined in ISO 50002, 2014, involves a systematic approach to understanding and improving energy performance. The Plan-Do-Check Act (PDCA) cycle is fundamental to this process. During the plan phase, the organization defines its energy policy, objectives, targets, and action plan, which includes identifying significant energy uses, SU, and establishing energy performance indicators, NPI. The do phase involves implementing the action plans. The check phase is crucial for monitoring, measuring, and analyzing energy performance, comparing it against objectives and targets, and evaluating the effectiveness of implemented actions. This includes reviewing data from energy meters, operational logs, and other relevant sources. The act phase involves taking actions to continually improve the NMS and energy performance based on the findings of the check phase. This might include revising objectives, updating action plans, or implementing corrective actions. Therefore, a comprehensive review of energy consumption data, operational parameters, and the effectiveness of implemented energy-saving measures as part of the check phase is essential for validating the initial energy audit findings and ensuring the NMS is functioning as intended to drive continuous improvement in energy performance. This process aligns with the directive to establish a baseline for energy performance and to determine how energy is consumed in the organization. Question 27. When conducting an energy audit in accordance with ISO 50002, 2014, an organization is evaluating two distinct energy-saving opportunities, ESO for its manufacturing facility. ESO Alpha involves a significant upfront investment in new machinery, projected to reduce energy consumption by 15% annually, with an estimated initial cost of $250,000 and an expected annual saving of $30,000. ESO Beta focuses on optimizing existing control systems through advanced software and training, requiring an initial investment of $50,000 and anticipated annual savings of $8,000. Beyond the direct financial returns, both ESOs are expected to contribute to improved operational reliability. Which of the following best describes the comparative financial viability and strategic consideration for selecting between ESO Alpha and ESO Beta, assuming a standard organizational hurdle rate for investment decisions? Option A. Both ESOs have comparable financial merits when considering the total lifecycle cost, and the choice between them should be based on non-financial factors such as employee training requirements and ease of implementation. Option B. ESO Alpha, despite its longer payback period, offers a more substantial absolute annual saving and a greater potential for long-term energy performance improvement, making it strategically advantageous if capital is available and reliability benefits are highly valued. Option C. ESO Beta presents a superior financial case due to its significantly shorter payback period and lower initial risk, making it the preferred option even if its absolute annual savings are lower than ESO Alpha. Option D. The decision should solely hinge on the payback period, with ESO Beta being the clear choice, as it requires a much smaller initial capital outlay and yields a return on investment much faster than ESO Alpha. The correct answer is B. ESO Alpha, despite its longer payback period, offers a more substantial absolute annual saving and a greater potential for long-term energy performance improvement, making it strategically advantageous if capital is available and reliability benefits are highly valued. Explanation. The core of performing a cost-benefit analysis for energy-saving opportunities, ESO, within an energy audit framework, as guided by ISO 50002, 2014, involves a systematic evaluation of the financial implications of implementing specific energy efficiency measures. This analysis typically requires the calculation of the payback period, which is the time it takes for the cumulative savings from an ESO to equal its initial investment cost. A simple payback period can be calculated using the formula: payback period equals initial investment cost / annual savings. For instance, if an energy-efficient lighting upgrade has an initial cost of $50,000 and is projected to yield annual savings of $10,000, the payback period would be /frac $50,000 $10,000 equals 5 years. However, a more robust analysis, particularly for advanced students preparing for an ISO 50002, 2014 audit, considers factors beyond simple payback. This includes the net present value (NPV) and internal rate of return which account for the time value of money. When comparing multiple ESOs, the one with the shortest payback period, a positive NPV, and an IRR exceeding the organization's hurdle rate is generally preferred. Furthermore, the analysis must also incorporate qualitative benefits, such as improved working conditions, enhanced corporate image, and reduced environmental impact, which, while not directly quantifiable in monetary terms for the payback calculation, contribute to the overall strategic value of the ESO. The selection of ESOs for implementation should be based on a comprehensive assessment that balances financial metrics with these broader organizational objectives and the specific context of the audited facility, aligning with the principles of continuous improvement in energy performance. Question 28. During an energy audit of a manufacturing plant, the audit team is tasked with establishing a baseline for energy consumption to quantify the savings from a proposed lighting upgrade. The plant operates on a variable production schedule, and its energy use is significantly influenced by both the number of units produced and the ambient outdoor temperature, which affects the HVAC load. According to the principles of measurement and verification, M and V, as described in ISO 50002, 2014, what is the most critical initial step to ensure the accuracy of the subsequent savings calculations? Option A. Obtaining detailed operational schedules and maintenance logs from the plant manager to understand historical energy usage patterns. Option B. Developing a comprehensive baseline model that accounts for key influencing variables such as production volume and outdoor temperature using historical data. Option C. Conducting a detailed walkthrough survey to identify all potential energy-saving opportunities without initial focus on baseline establishment. Option D. Immediately installing sub-metering equipment on all lighting circuits to capture granular consumption data post-implementation. The correct answer is B. Developing a comprehensive baseline model that accounts for key influencing variables such as production volume and outdoor temperature using historical data. Explanation. The core principle of measurement and verification, M and V, as outlined in ISO 50002, 2014, is to establish a baseline for energy consumption and then quantify the energy savings achieved by implementing energy efficiency measures. This involves defining clear, measurable, and verifiable parameters. For a facility undergoing an energy audit, establishing a robust baseline is paramount. A baseline represents the energy consumption pattern of the facility before the implementation of any energy efficiency projects. This pattern is typically influenced by various factors, including production levels, operating hours, weather conditions, and other relevant variables. ISO 50002, 2014 emphasizes that the baseline should be representative of typical operating conditions and should be adjusted for any significant changes in these influencing factors. The goal is to isolate the impact of the implemented measures from external variations. Without an accurate and appropriately adjusted baseline, the calculated energy savings will not be reliable or credible. Therefore, the process of defining and documenting the baseline, including the identification of key variables and the methodology for adjustment, is a critical first step in any M and V plan. This ensures that any subsequent deviations in energy consumption can be attributed with confidence to the energy conservation measures rather than to changes in operational or environmental conditions. The quality of the M and V outcome is directly dependent on the rigor applied during the baseline establishment phase. Question 29. During a comprehensive energy audit at a manufacturing facility, an auditor is tasked with evaluating the performance of several large-scale induction motors driving critical process equipment. The auditor needs to establish a precise understanding of the current operational efficiency of these motors to identify potential energy conservation measures. Considering the principles outlined in ISO 50002, 2014 for effective energy auditing, which of the following methods would provide the most accurate and actionable data for determining the actual in-service efficiency of these motors? Option A. Comparing the motor's operating parameters and energy consumption against industry-wide benchmarks for similar motor types and applications. Option B. Direct measurement of the motor's electrical input power and mechanical output power under its typical operating load. Option C. Calculating efficiency based on input electrical power and a theoretical estimation of the mechanical load derived from process data. Option D. Utilizing the nominal efficiency values stated on the motor's nameplate and adjusting for estimated load conditions. The correct answer is B. Direct measurement of the motor's electrical input power and mechanical output power under its typical operating load. Explanation. The question focuses on identifying the most appropriate method for assessing motor efficiency in the context of an energy audit according to ISO 50002, 2014. The standard emphasizes a systematic approach to identifying energy-saving opportunities. While direct measurement of input power and output mechanical power is the most accurate method for determining actual motor efficiency under operating conditions, it requires specialized equipment and can be disruptive. Nameplate data provides a nominal efficiency that may not reflect actual performance due to age, operating conditions, and maintenance. calculating efficiency based on input power and load estimation, while useful for preliminary assessments, introduces significant uncertainty. Comparing motor performance to industry benchmarks for similar applications is a valuable step in identifying potential underperformance, but does not directly quantify the efficiency of the audited motor itself. Therefore, the most direct and robust method for an energy auditor to establish the current operational efficiency of a motor, as per the principles of ISO 50002, 2014 for detailed assessment, is through direct measurement of its electrical input and mechanical output. This aligns with the standard's requirement for data-driven decision-making and accurate identification of energy losses. Question 30. When conducting an energy audit on a manufacturing facility in a temperate climate, an auditor is tasked with normalizing the facility's natural gas consumption for space heating across several years to account for seasonal weather variations. The facility's operational schedule and production output remained consistent throughout the audit period. The auditor has collected historical daily average outdoor temperature data. According to the principles outlined in ISO 50002, 2014 for energy audits and the common practices for degree day analysis, what is the most critical factor to establish for accurate normalization of heating energy consumption, ensuring that the analysis effectively isolates the impact of weather on energy use? Option A. The correlation coefficient between energy consumption and average daily temperature to determine statistical significance. Option B. The average daily temperature for each month to calculate the monthly heating degree days. Option C. The selection of an appropriate base temperature that reflects the building's thermal characteristics and heating requirements. Option D. The total number of days in each month to adjust for variations in the length of reporting periods. The correct answer is C. The selection of an appropriate base temperature that reflects the building's thermal characteristics and heating requirements. Explanation. The fundamental principle behind degree day analysis in energy auditing, as per ISO 50002, 2014, is to normalize energy consumption data for variations in external weather conditions, primarily temperature. This normalization allows for a more accurate comparison of energy usage over different periods, isolating the impact of operational changes or energy conservation measures from the influence of weather. The base temperature, often referred to as the balance point, is a critical parameter in this analysis. It represents the outdoor temperature below which heating is required and above which cooling might be needed, though for heating-focused degree day analysis, it's the threshold below which heating energy consumption is assumed to increase linearly with decreasing outdoor temperature. A common approach is to use a 5 degrees C, 60 degrees F, base temperature for heating degree days HDD and a 3 degrees C, 65 degrees F, base temperature for cooling degree days CDD. The calculation of HDD for a given day involves subtracting the average daily outdoor temperature from the base temperature, but only if the average temperature is below the base temperature. Otherwise, the HDD for that day is 0. Similarly, CDD is calculated by subtracting the base temperature from the average daily outdoor temperature, but only if the average temperature is above the base temperature. The total degree days for a period are the sum of the daily degree days. The key insight for an energy auditor is that if energy consumption is plotted against degree days, a linear relationship should emerge, allowing for the identification of baseline consumption and deviations from it. Without a correctly identified base temperature, the normalization is flawed, leading to inaccurate assessments of energy performance and the effectiveness of implemented measures. For instance, using a base temperature that is too high for a particular building's heating characteristics would underestimate the impact of colder weather, and vice versa. Therefore, selecting an appropriate base temperature is crucial for the validity of the degree day analysis.